All right, so we're getting into equilibrium now. This is probably one of the more important topics that we cover in this class. So let's have a look. So whoever figured out how to get that pole in the ground there, they did some equilibrium type analysis. Now they might have ran some numbers on paper, or they might have done it 100 times before, so they have some kind of common sense on how to put it in properly. But at some level, they were doing some equilibrium analysis on that, okay, to make sure that that thing doesn't move, okay. So you can see the 3 cables up at the top. Those are cables, right? So what are they doing? They're pulling, okay? So they're doing that. So somebody said, well, if those cables are going that way, I better go this way. Or if I don't, I'm going to have a problem, okay? That's kind of, what was going on there, right? So let's look at this in a more formal kind of way. Now, equilibrium, I'm on page 378. Equilibrium is when the net acceleration is 0. So that means A is 0, and if A is 0, when you apply that Newton equation that we mentioned earlier, sum of F then is 0. So the sum of forces is 0. Now from that we can conclude with our vectors that sum of Fx is 0, sum of Fy is 0, sum of Fz is 0. Also the sum of moments anywhere on or off the object is 0 too. Because not only do we have linear acceleration, A being 0, we also have angular acceleration, which is called alpha, that's 0 too. All right. So what we can do now is we can start analyzing these objects a little bit more thoroughly than we've been doing here so far. If we're in 2 dimensions, we can generate 3 equations to figure out some unknown forces. Sum of Fx, sum of Fy, and sum of moments about anywhere you want to take it is 0. Okay. Now in 3 dimensions you get 6 equations, force equations for each of the directions and moment equations for each of the directions. So if you can handle up to 3 unknowns in 2 dimensions, if you have more than that, it's called statically indeterminate, and then you have to start using more advanced methods to figure out what those unknown forces might be. So what we're going to do here in our engineering world is we're going to have an object, let's say a beam, and we're going to figure out what forces are applied to it. We're also going to have to hold the object down with pin joints and rollers and brackets and things like that. So we're going to generate a free body diagram with unknown reactions. So we're going to use statics, this equilibrium analysis here that we're doing, to find the unknown reactions. Once we find the unknown reactions and we already have the forces that are applied, now we know every force acting on that object, and now we can design it so it's strong enough to withstand those forces. Okay? That's kind of the sequence there. So step 1 is to figure out what the applied forces are. Then you do an equilibrium analysis and figure out what the reactions at the supports are. Then after that, you start going inside the object and designing it so that it's strong enough to handle all this stuff. Okay? So that's kind of the big picture on this. Now there is a little deal with signs, and we talk about this a lot. I'll mention it. It'll probably make more sense when I show you an example of this, but I'll at least mention it now. Okay, the signs that you put into the equations, they're based on what direction you assume the forces act. All right. The signs you get out of the equations, which are the signs of your answers, tell you whether or not your assumption of direction initially was correct. Okay, so the signs mean different things depending on where you use them. When you put them into the equations, they indicate the direction you assume things act. However, the signs you get out of your equations, the answers, indicate whether your assumptions were right or not. Okay. Here's just a quick example, and we'll touch on this more when we're actually running numbers. Here's a beam, 800 Newton force right in the middle. I assume both of the reactions are up. Okay, so I assume that RA is up. Now, what I can do, and we'll get into this here in a minute, but I can take a moment about B to analyze this, and when I did that, I got 800 newtons times 2 meters, and that's counterclockwise, so that went in as a positive. And then I have this one, which is going to create a clockwise moment there, so that would be negative 4RA. So when I assumed RA was up, the moment it creates about point B is positive, excuse me, is negative, it's clockwise. So that's why that's a negative 4RA. I run the numbers and my answer is positive. That positive answer means I assumed correctly. It does act up. That's what that positive means. Now, had I made the opposite assumption and assumed that RA was down, what would have happened when I did that moment about B is that downward RA would create a counterclockwise moment, which would be positive. So that goes in as plus 4RA. When I solve for RA, I get a negative answer. The meaning of the negative is it doesn't act down, it acts the other direction, it acts up. Okay. So that's what signs do in these equations. You'll notice that regardless of which way I assumed it acted in the free body diagram, I got the same answer. It's 400 newtons up, either way. Okay. So just be aware of what these signs mean and how we use them. Okay. So we're going to spend a little bit of time on equilibrium here. So we got any questions I want to just set there? And we'll do more examples of that. I just want to mention that before we started. Okay. Okay. We're going to, yeah, sure thing.
RB, what are you assuming? The up arrow, is that just representing the normal force, or?
Yeah, RB there is, I didn't, on RB or RA? I'm sorry. RB, yeah, that's a roller, so I'm assuming that force is up.
Okay.
Perpendicular to the flat surface that the roller's sitting on.
Okay.
Is that good? All right. Okay. Good. So why don't we start with some simple beam and column analysis. By simple beams and columns, I mean things that are horizontal. So that's a beam, the horizontal member there. And the vertical one is a column. These are simple because they're vertical and horizontal. Okay, so that's what I mean by simple beams and columns. Okay, you might think of that as being a simple column, just a vertical column, even though it's a power pole, I think. There's inside Takina Hall. Those are simple. That's a simple beam running right there. That's actually a T-beam. It's a T right there. Okay, T-beam, pretty simple horizontal beam. That bridge could be analyzed like a simple beam. There's a couple of simple beams. You see the simple beam on the flatbed trailer, but you also see the flatbed trailer itself. See, even the mechanical engineers, you do a lot of structural analysis. We don't quite call it quite like the civils do, but it's the same idea. That flatbed trailer is a beam. You analyze it like that. Okay. So let's start off with a simple beam analysis. So I'm on page 400. So how about taking 1 minute and turning that beam into a free body diagram? Okay. Now the thing with this is don't overthink it. You see a certain type of joint, replace it with the forces that it should be replaced with. We're assuming the weight of the beam is 0 on this one. Got something like that? Pin joint, two forces, one horizontal, one perpendicular, or one vertical. Roller, a vertical force. I mean, that's it, and that's all the thinking I give that, okay? I'll do my thinking later, okay? We good with what's up there? Because that is, it's a simple step, but it's important. So, any questions on that?
Why don't we need something for the forces like the Newtons on it?
The applied forces, I don't know what you mean. Yeah, well, they're already there. I mean, we have forces.
So there's nothing extra to draw for them.
Yeah, right.
What's it called, center of gravity?
Yeah, what's going on? We're going to ignore the weight of the beam on this one, and that's a good question. You know, if you're given the weight of the beam, you put it at the center of gravity or the weight of the whatever. If you're not, you're pretty much assuming that it's being ignored, and probably because it's insignificant compared to the forces that are applied. Okay, so yeah, we're assuming this beam weight is 0. Okay. All right. Okay, now let's find the reactions then. Okay. Now, here's the deal. There are not infinite possibilities of how to do this. There are 3 possibilities of how to do this. Sum of fx is 0, sum of fy is 0, sum of moments is 0. So what I want to do here, I want to keep my calculations as simple as I can. So what would be a good equation to start with if I want to have one unknown in my equation? Okay. I think I've heard the one correct answer so far. I'm not quite sure. There seems to be a little different opinions here. That's always good, though. Different opinions are good. Will that work? Okay, I think that'll work, eh? Now, how about if you go with sum of fy equals 0? How many unknowns are you going to have? You're going to have 2, and I don't want to, you know, now if I have to, I'll run that, but I don't want to. I want to be lazy and keep my equation simple. So I'd probably start with sum of fx equals 0. Okay. Now, write down sum of fx equals 0. Take the time to do that. Don't rush here. Sometimes people ignore that step, and it can get you into trouble sometimes. Now, if I got sum of fx equals 0, what do I got? What goes into that?
4,000.
Yeah, there we go. A little bit of trigonometry there. What I want is I want the adjacent side to the angle, which would be the cosine of 30. Now, what's the sign on that going to be? Yeah, it'd be negative, right? There we go. So now we can find RAX. And I don't know what that comes out to be on top of my head. It's 17, 34, 64. I don't know. 30 times 4,000. Okay. Yeah, okay. So that gets me RAX. That's 3,464 newtons. No, that came out positive because, and why don't I go ahead, let's do the steps. It's worth it because what we're going to do, we're going to take that 4,000 cosine 30 to the other side of the equation. Okay, and then, so RAX is positive, 3464 newtons. Now, the positive means I assumed it's going to the right. My answer came out positive. It is going to the right. Okay. So that's 3464 newtons. Okay. All right. So I've used sum of fx as 0. Now I need another, so I found one of the unknowns. I still got RAY and RC. What do you think? What would be another equation I could run that will have only one unknown? Moment about. We're going to take the moment about. I think the moment's the right way to go, but you have to think about where to take it about. Moment's about C or A, right? And what we're doing here, and a very good strategy on a lot of these, you can do C or A. Yeah, I've got a roller at C, I've got a pin joint at A. If I take the moment about A, I'll eliminate both of those unknowns. Because they go right through A, I could do the same thing at C. I could do a moment about C or A, either one. And see, often when you have a pin joint, a good way to start is to take a moment about it because you immediately eliminate two unknowns. Okay. Now in here, all I got to eliminate is one unknown because I've already found REX. It's no longer unknown. I can take a moment about A or C. It doesn't matter. Okay. What did I do here? I did that. Yeah, I did a moment about A is what I did. C would be fine also. It doesn't really matter. But I've got A all set up to go, so let's look at A. So I got sum of MA equals 0 equals, because I know that the thing's in equilibrium. See, if the sum of moments about A is not 0, that thing will start to rotate, okay? And the purpose of these supports is to prevent that. So when I take moments about A, I've got 6,000 newtons times 1.2 meters. And I've got a clockwise rotation, so that's a negative. Okay, so that negative sign means it goes clockwise. As I work my way to the right, I've got RC, 1.2 and 1.8 makes 3. That's going to go counterclockwise, so that gets a plus.
3.5?
What's that now?
Oh, no, never mind.
And then I've got sine 30 because that's the opposite side. It's really, if I look at a triangle, it's over there, but I want to put it at D, so I'll put it right where I drew it. That's opposite the angle, so that's a sine 30. 4,000, 1.2, 1.8, 1.2 makes 4.2 meters. That's coming around that way, clockwise, so that gets a minus. Okay, so I've got the 3RC, that's the unknown. I can take the other two terms to the other side of the equation. They're both negatives on this side of the equation. So when I take them to the other side, they become positives then. And then I just work through the calculations and I get RC as 5,200. Doing all right with that? Any questions?
Should it be Newton meters or units?
It would be newtons, because for two reasons. One is it's a force.
Yes, it's 3 meters.
Yeah, okay. It's a force, that's why it's newtons. And yeah, I understand what you're saying about the units. And it's kind of hard to show with the unknowns, to kind of label unknowns with a force. Yeah, Kristen?
Wouldn't the 15,600 still be Newton meter?
Yeah, it would. And there's the 3 is actually 3 meters is really what it is. So I might be getting a little sloppy with that. So yeah, you're right. Now the final answer is newtons, but there is a step in there where things are Newton meters. So I should probably clean that up a little bit. I kind of took the meters out of the 3, so I also took it out of the 15,600 is what I did. Okay. So we good with that? Questions on that?
So if you could find moment about A or C,
Mm-hmm.
would it be the same?
Well, the sum of them would be 0. You know, it's the moment about any point is 0. If you took the moment about C, though, it'll be different than A because you start changing the moment arms to the forces. And what you'll end up finding is not RC is 5,200, but you'll find RA, which will be a different number, I guess. Is that a good answer? Or?
Yeah.
Is that good?
Well, you might have already said this, but how do we know that RC is going to come?
RC is going, well, first off, I don't know. I'm assuming.
Oh, that's not what you're assuming.
Yeah, and see, when I push up here, if I'm holding a yardstick and I push up on it on the other side, you can see which way that's going to go, right? So I have to kind of get myself oriented like y'all are. It's like that. Other questions? All right. Now, what's the easiest way to find RAY, do you suppose?
So it's R equals
Yeah. How about like that? Okay. Sum of Fy, set that equal to 0. I wouldn't do a second moment equation because it's more complex. Force equations are easier. After I found RC is 5,200, I'll just go sum of Fy. I only have one y unknown, so I can solve for it. So RAY comes out to be 2,800. Okay, so I did a sum of fx. I found the 3464. Then I had two y unknowns, RAY and RC. So I had to do a moment equation about A, and I found RC. Once I know RC, I can go sum of Fy and set that equal to 0. And that's the basic equilibrium process there. That's how you work through them. Our goal here is to find all the forces at the supports. And once we have all these forces, we could do some things that you'll learn if you take strength of materials and end up designing that beam to withstand them. But that's kind of the next, we won't get all the way into that in this class. A little too far to go. Okay. So we're good with that? Okay. All right, now if I want to check, I could take a moment about a point other than A or C, and a moment about any point on the object or off the object, a point about anywhere, or excuse me, a moment about anywhere ought to be 0. So to check it, I just took a moment about D. That included both of the reactions in the equation, which allows me to check them. I might have a little bit of rounding error in there, but I don't think I did on this one. But you know, if you get just a little answer that isn't exactly 0, I wouldn't get too worried about it if it's small compared to the applied forces and all that. And I got 0, I got it to 0 out, so that's good. So we got any questions on that? Okay. And so that's the basic process. Now we're going to look at a few variations on this, of course, because we get into more complex problems, but that's the basics of it right there. You're going sum of moments and sum of forces. And by using those different things, you can find the forces on the reactions, or at the supports, I should say, which we call reactions. All right, so we good? Now, let's look at what would happen if we had made different assumptions about the directions of the reactions. Now, I don't think you need to copy this down. I just want you to kind of follow it, because this bit with the signs, I just want to illustrate that now. So what I have here is the exact same problem. I've just turned all of the reactions the opposite direction of what I assumed initially. And I'm making some kind of silly assumptions here, but all the same, it'll help illustrate this idea of signs, okay? So let's say I'm doing this. I'm taking all those reactions, I'm turning them in the opposite direction of what we just assumed. All right, when I go sum of fx equals 0, now instead of rax, I'm going to have negative rax, because I've got rax pointing to the left this time. That's how I assumed it. So that goes in as a negative now. So I've got minus rax minus, because this is also to the left, cosine 34,000. When I bring rax to the other side of the equation, it becomes positive, and that number is negative there. Okay, so I assumed it acted to the left, but my answer came out negative. That means no, it doesn't act to the left, it acts to the right. Okay, so even though I assumed the wrong direction for rax, I end up getting the same answer as before, the correct answer. It acts to the right. You just have to interpret the signs and what they mean. Okay. So this negative here means it acts to the left, or I assume that anyway. The negative on the answer means no, it doesn't. It goes the other way. Okay, that's all it means. Okay. All right, and so once again, if I do a moment about A with these set of assumptions, I've got 6,000, the moment about A times 1.2, that's negative because it's clockwise. I've got RC acting down, so that becomes negative 3 RC. 1.2 and 1.8 get me 3 clockwise, negative, okay? I've got the sine of 30 times 4,000, that opposite side, so I use the sine, times 4.2. Everything's negative on this. When I bring the negative 3RC to the other side of the equation, it becomes positive. When I solve, it becomes negative 5,200. That means no, it's not down, it's up. Okay? That's the meaning of the signs. Okay? We got any questions on that? Okay. We take a break here though for about, we'll start at 5 till, start up again. Okay. So why don't we do one of these here?
Yeah. So I feel pretty good about that. Yeah.
How about this one, 261? We are on page, it's in the homework section, page 13. I won't have you turn this in, but let's just go through it, see if you can do it. Page 13. You can just do it in the margin or whatever. So there it is. We've got a beam. We got the 7,000 newtons acting down. We're ignoring the weight. So we got a couple fittings there that are holding it up. So what's the first thing we do on these things? There we go. We always do that. Okay. So take literally a minute. Turn that into a free body diagram.
Yeah.
So page 13.
I'd say these. Yeah.
Okay, free body diagram. You got the force on there. Okay. Everybody got a free body diagram? We're good? Okay. And you know, quite seriously, free body diagram, pin joint, REY, REX, cable, poles. There's my free body diagram. I'm done. Okay, that's it. And I just want to encourage you, don't overkill those. Just do that and you're done. Yeah, question?
You have to circle it too.
What's that?
You have to circle it as well.
Well, the circle, I put a circle on it so I see where the contact forces
Okay.
are. You don't have to, no. It's a good metal thing, so you don't miss anything. But on that one, bang, bang, we're done. Yeah.
The thing on the top of the cable on B, is that where we're just ending the?
Yeah, it's cable BC, so you could call that TBC if you wanted to. Yeah. Other questions? We good? All right. So there we go. See, I call it TBC here. Okay, what do we do next? Now remember, there aren't infinite possibilities on what you do next. There's 3 things you could do next. Those are the 3 things. So figure out an equation you can use that will only have one unknown, because it's just, the calculations are simpler when you do that. So find an equation that has only one unknown and solve it. And start it out as I started it out there. Sum of fx is 0, sum of fy is 0, sum of m about somewhere, I've got some space in there, is 0. So come up with an equation that will get you one unknown, so that way you can solve it. But give me a negative number.
Yeah.